Welcome. This is a time series analysis course. My name is Nicoleta Serban. I'm associate professor in the Stewart School of Industrial System Engineering. This lecture is on multivariate time series, and in this lesson, I will introduce the VAR model, the most common model used for multivariate time series. The VAR model, or the vector auto-regressive model, made famous in Chris Simms' paper Macroeconomics and Reality, published in Econometrica in 1980, is one of the most applied models in the empirical economics. Chris Simms received the Nobel Prize in Economics in 2011. Before VAR, the relationship between time series was captured in a more exogenous manner using standard regression analysis models. Simms argued that such conventional macro models were incredible, in quote. That means they were based on non-credible identifying assumptions. While the VAR model was highlighted in a Simms 1980 book, it was slowly adopted, but now it is one of the most commonly used models for applied macroeconomic analysis and for forecasting in central banks. This is a model you need to put on your list of analytic skills if you are working or will be working in these fields. The vector autoregression, or VAR, model is also easy in the analysis. I'm sorry. The vector autoregressive model, or the VAR model, is also easy to understand and to implement in the analysis of multivariate time series. It's a natural extension of the univariate autoregressive model to dynamic multivariate time series analysis. It often provides superior forecasts to those from univariate time series models and elaborate theory-based simultaneous equations models. Forecasts from VAR models are quite flexible because they can be made conditional on the potential future path of specific variables in the model. In addition to data description and forecasting, the VAR model is also used for structure inference and policy analysis. I'll discuss and illustrate these properties of the VAR model throughout this lecture. The VAR model with lag P for n variate time series, yt, is defined similar to the AR model. Yt depends on yt minus 1 up to yt minus p linearly. Now, the coefficients are matrices pi 1, pi 2 to pi p, which are n by n matrices of coefficients. The error term epsilon is assumed to be white noise, and the covariance with the covariance matrix sigma. For illustration, consider the bivariate VAR2 model, meaning that we have two time series and the autoregression order is 2. The time series is a vector of two time series y1t and y2t. The matrices pi 1 and pi 2 are 2 by 2 matrices of coefficients, indicating that y12 depends on the lags y1t minus 1 and y1t minus 2, and also depends on the lags y2t minus 1 and y2t minus 2. The error term is a vector of two error terms also. We denote the contemporaneous covariance of two error terms by sigma 1, 2, where the lagged covariance of the error terms is 0. That is, the model captures the lagged relationship between the two time series through the AR part and the contemporaneous relationship through the error term. To note that the VAR model, also called the unrestricted VAR model, has the same set of regressors for both y1t and y2t for both time series. This assumption is useful in the estimation of the coefficients, as we'll learn in the next lessons. A stable VAR is the extension of the concept of causal AR model. First, the AR model presented in the previous slide can be rewritten as pi of L times the vector of time series, where L is a multivariate operator, an extension of the B operator we learned for univariate time series. A VAR P is stable if the roots of the VAR equations, as provided on the slide, are modulus greater than 1. Note that this is a similar definition to the definition of causal ARMA. We can further translate this definition into that the eigenvalues of the companion matrix F have modulus less than 1. To note that the difference between the two I will note here the difference between the two equivalent definitions. For the latter, again, the eigenvalues are smaller than 1 in modulus. It is important to remember that since the R function used to evaluate stability provides the modulus of the eigenvalues of F, not the roots of the VAR equation, we will seek to values of smaller than 1 in modulus in order to assess that the VAR process is stable. Importantly, a stable VAR of order P process is stationary with time invariant means, variances, and autocovariances. This is similar to the causality property of the ARMA model. If you recall, the causality implies stationarity. The same here, stability implies stationarity. For the simple bivariate VAR1 model, the stability translates into the equation depending on the coefficients pi11, pi22, pi12, and pi21, as provided on the slide. If the cross terms are 0, then the stability property reduces to univariate causality conditions for each time series. In a different lesson, we'll learn about generalization of the VAR model in that we can add to the VAR components a deterministic component, often referring to trend and/or seasonality, and exogenous relationships to the other time series. This model is particularly useful when the time series present trends and/or seasonality. It can also be useful when we believe that one time series predict or lead another, but not the other way around. In this summary, I introduced the concept of stability of a VAR model with a more general framework of presenting the vector auto-regressive model. Thank you. Welcome. This is a time series analysis course. My name is Nicoleta Serban. I'm Associate Professor in the Stewart School of Industry and System Engineering. This lecture is on multivariate time series, and in this lesson, I'll illustrate VAR modeling with a simulation study. In this example, I'm simulating a VAR model because I'm using the multivariate norm function in R. I need to first load the mass library. This command can be used to simulate multivariate normal data. Here, I developed an R function that can be used to simulate a VAR model of order 1. You can also use this example as an illustration of how you can write your own functions in R. The name of the function is var.sim, and the inputs in the functions are phi, sigma, y0, and time, where phi is a matrix of coefficients, sigma is the covariance matrix of the error terms, y0 is the starting vector of values, or seed values for the time series, and time is the length of time. First, n is the dimensionality of the time series, or the number of time series in the vector time series. This is the vector of the multivariate time series, which starts with y0. Then it builds with each time point by iterating over I and simulating the multivariate time series for each time point or index I. The function returns this multivariate time series. To apply this function, we need to first create the input in the function consisting of phi, sigma, and y0 as provided on the slide. Phi, as defined here, is a diagonal matrix, thus there are no lead-lag relationships between the time series. I will note that the multivariate time series has a dimensionality of n equal to 3, since phi is a 3 by 3 matrix. The covariance matrix of the error terms is not diagonal, thus we have contemporaneous correlation between the 3 time series. Last, we apply the VAR sim function with this input. In this simulation, I consider only 3 time series, but we can extend this to more than 3 time series since we can add more rows to the coefficient matrix and to the covariance matrix. Next, we look at the time series plots along with the ACF and PACF plots for all the 3 time series. Instead of writing the 3 commands for plotting the 3 plots for each time series, I iterate here over I from 1 to 3 with the same R commands, but for each I change the time series to be plotted and the titles of the plots. This is the output of the R code for the plots for the 3 time series. The first 2 time series seem stationary, but not the last one. This is because the error coefficients of the AR1 is stationary only if the coefficient is smaller than 1, is different than 1. In this case, the coefficient is very close to 1. We observe significant autocorrelation at lag 1 for series 1 and 3 in the PACF plot, suggesting an AR1 model. The ACF plot for the second time series shows no large autocorrelation, while the first time series, first time series there may be autocorrelation as the sample ACF value for lags 1 and 2 are outside of the confidence band. For the third time series, the ACF points to non-stationarity. How about cross correlations? We can use the ACF and the PACF-R functions with the unit of the union of the 3 time series. These are the ACF plots. Again, on the diagonal, we have the autocorrelation plots, and off diagonal, we have the cross correlation plots. When interpreting the cross correlation plots, you will need to be careful that some of the plots have an increasing lag and others have a decreasing lag. The cross correlation plots show little lead lag correlation. The correlation at k equal to 0, or so-called contemporaneous correlation, shows to be somewhere outside of the confidence bands for most of the cross correlation plots. Note that we indeed simulated contemporaneous correlation since the covariance of the error terms is not a diagonal matrix. Last, we can establish whether this is a stable VAR process by first fitting the VAR model and looking at the summary of the fit, which provides the eigenvalues of the companion matrix F. The output of interest is provided by the R roots of the characteristic polynomial, which are the eigenvalues of the matrix defined in the previous lesson. Note that these are not the roots of the VAR equations. Thus, to check stability, all these roots will need to be smaller than 1, which is the case in this example since all eigenvalues are indeed smaller than 1. In summary, in this lesson, I illustrated the VAR model with a simulation example. Thank you.